So we're going to see how this works here with sort of doing the lecture as a video for you guys to check anytime. So we're going to start talking about gravity here, which is a relatively straightforward topic, which makes a good way to sort of trial some of this stuff out. Because almost all these problems we've already done before in some way or another. We're just adding sort of a new way of calculating a force. We're going to talk in this section about gravity with the idea of forces in motion. So using like Newton's F equals ma to sort of to solve problems that way. And then the second half of the unit, we'll talk a bit more about energy momentum, right? So kind of applying all the concepts that we've seen before now to a specific situation. Gravity is also a little bit of a special case in the sense that it is sort of the foundation of a lot of stuff we've talked about already and sort of where it came from. And so part of this as well is sort of understanding the historical context, so you know where some of this stuff came from. So a little bit of today is also some history, which is what we're going to start with first. So the first thing to note is that the idea of gravity is obviously not something that's just a physics concept. The equations related to it are, but the results of it are something that were studied long before it was understood why, specifically with astronomy. And so gravity's origins really come from observational data from the scientist here who gathered the observations of how stars and planets moved, and then his assistant who then analyzed that data and sort of found some patterns that were repeated. And so we're going to show where these three Kepler's laws come from, but for now I'm just going to state them so you have them listed. If the slide loads, which it may not. That one loaded. Let's try this. Maybe. Okay, so now it's actually loaded, which is helpful. So anyway, the first Kepler's law that we're going to sort of show where it comes from later is that planets move in elliptical orbits. There's a lot of terminology that you should know related to elliptical orbits, which hopefully is familiar from geometry classes, right? The idea of the minor axis and the major axis and the focus or the foci, because there's two for an ellipse, really are the keys to sort of relating elliptical orbits to a more specific circular orbit, right? Circles are special cases of ellipses. So planets always move in elliptical orbits in general. In our solar system, the ellipses are very close, but not exactly circular, right? And so that's the first thing that sort of the data showed. They weren't perfect circles. The second one, and this one's very tough to describe without the mathematical behind it. So just read the sentence and look at the picture, really. We'll talk more about this one because once you understand the math of what causes this, it's really not as bad as it sounds. But the key is when you're close, you move fast. When you're far, you move slow. That's Kepler's second law. So if you're in a circular orbit, you never change your speed because you're always the same distance from the thing you're orbiting. But for something like a comet that has a highly elliptical orbit, it moves very, very slow when it's far away and much, much faster when it's very close to the sun. And again, we'll show where this comes from later. And then the last one, the most obviously mathematical one of Kepler's laws, and the hardest really to imagine how you'd figure out something this way just from data, is this statement right here. And this is the really important one for some calculations that we'll see later. But observationally, it was clear from the data, from Kepler's data, that the square of the orbital period, and that's a key word that you need to know if you might have forgotten, right? Period is the time it takes to do an orbit. The square of the period is proportional to the cube of the semi-major axis length, which is basically, right, really, this is the radius of orbit. Oh, there it goes. Right. Because we're not going to really talk about elliptical orbits a whole lot. So when really this means the period is based on how far you are away. Right. And then this graph right here just shows that data for our solar system. Notice how this is a logarithmic scale. So that's where this right here is 3/2, and that's the cube and the square. It's a logarithmic scale. So don't worry too much about that. We'll show the mathematics behind that a little bit more. But observationally, that was sort of something that Kepler found out. Okay, so the next thing, we're going to be doing a lot of problems involving astronomy data, because that's where a lot of these gravity calculations are relevant. So this table, which is in your book as well, is super relevant to keep on hand, right? If it asks you for like the mass of the moon or the orbital period of the moon or anything like that, this table, you can look it up to use it, or Google, right? Just keep that in mind. This is a reference. So we already talked about this a little bit, right? Circular orbits are what we're going to solve 99% of the problems with, just because it makes the math a lot easier and still illustrates the concepts. So basically, in circular orbits, right, Kepler's third law is much easier to understand, right? Period squared is proportional to radius cubed, and we move at a constant speed, and the sun is at the center, right? Much simpler to understand, but the same idea. Okay, so that's sort of pre-actual physics, but just kind of the background for sort of what we're going to talk about. Isaac Newton had access to this data. That data predates him by a couple decades. And so with that data, that's how he was able to sort of arrive at the conclusion of what was causing it. Right? And so he said, okay, well, the reason the moon goes around the Earth is because there's a force that attracts it to the Earth, just like the apple falling to the Earth as well. But the moon is moving quickly to the side, so it can't actually hit. Right? So with that kind of idea in mind, this is the mathematical bit that will lead to some practice problems we're actually going to do. He proposed with, again, only really Kepler's laws as evidence. He said that all objects, right, this is all objects, right, any object, so not just like a planet and a sun or a planet and a moon, any objects. If any objects are a certain separation distance apart, there's an attractive force between the two, right? And notice F1 on 2 and F2 on 1, this is from the third law, right? Must be the same. And notice as well, right, distance between centers, not surface to surface, but center to center. And there's a new constant in here, this capital G, which is not the same thing as little g. Right? Little g is specific to the Earth. That's why it's called the gravitational acceleration on the Earth's surface. Capital G is universal. Right? It relates any two objects, any distance, any mass, anywhere. Okay? And so that is on your AP sheet, so you don't need to have it memorized, but just remember capital G and little g are not the same. Notice as well, very small, right? 10 to the negative 11th. This is why if you have two books sitting on a desk, you don't see them slide towards each other, right? Yes, there's a force. No, it's not a very strong force. We'll see a couple of practice problems with that. A terminology bit to recognize, right? It's an inverse square law, right? As the distance gets bigger, the force gets smaller, but it's quadratically, right? Inverse square. That's an important term to just kind of recognize. And notice the axes labeled, right? 2r and 1/4 the force. Okay. So again, just to really emphasize the size of this force, right? If you take two 1 kilogram masses, put them a meter apart, that is a force of 10 to the negative 11th newtons. Now, we're used to dealing with forces that are, maybe 1/100th of a newton as the small scale. This is a billion times weaker than that, right? You don't notice this in everyday life. You need a lot of mass. That's why most of the problems we do when you talk about gravity are going to involve things like moons going around planets or planets going around suns, because that's the only place where the mass is big enough to really matter. Okay? Doesn't mean it's not calculable elsewhere, just it's not as important. Let's do some practice ones now. So here, we know the force X on Y, and we want to know the force of Y on X, right? So we want to know Fy on X. And this is really quite straightforward, because all you have to recognize is look at these subscripts. That's a Newton's third law pair, right? A on B and B on A, the interaction between the two. Once you recognize it's a third law pair, then you know Newton's third law tells us that it must be the same, right? Yes, planet X is more massive than planet Y, but the mass contributes to the interaction between the two, not like it doesn't, the fact that planet X is more mass doesn't mean that planet Y feels a bigger force, right? The interaction is bigger between both of them equally from the third law, right? So same as. Okay, so a bit more math, right? We were told these two asteroids have a 1 million Newton force between them. Now we're going to double the distance and ask what happens to the force. Well, we know that in general, right, that's our law for forces. And the thing that we're changing is that, right, the distance. So if we double r, right, that's 2r, right? And since it's in the denominator, we get a 2r squared, which is the same as 4r squared. And so it's this factor right here that matters, and that's a factor of 4 in the denominator. So we should just do 1 million divided by 4 and get 250,000, right? Very important to be able to sort of reason proportionally without having to sort of calculate it out. You don't want to have to plug in values like g and sort of calculate what m1 times m2 is. Just recognize that doubling the forces means that r squared gets a factor of 4, or doubling the radius rather. Okay, so now here, a little bit more complicated. We want to know the net force, right? The net force. So in other words, we have to figure out what forces are there. Well, there's an interaction here, right? The star of mass 2m is interacting with the star of mass m, but there's also an interaction here, right? Just like anything else, there are as many forces as there are interactions. So we've got this one, which I'm going to call F1, because it's with the star of mass just 1m. And we also have, this one, which I'm going to call F5 because it's with the star of mass 5m. Now, if we want to know the net force, we just have to add those vectors, which in this case, because they're in a straight line, really isn't all that bad. So let's calculate what those two forces are, and then we can do it, right? F1 is g times m1, 2m, times m2, which is m, and we're going to make each one of these units r. Right, so each one of those units is r. So we have 2r squared. F5, on the other hand, right, we have 1, 2, 3, 4. Right, we have 4 radius units difference. G is still the same. Now it's 5m and 2m and 4r squared. Right? So that's just setting it up. Now we just need to simplify. So here we get a factor of 2 over 2 squared, right? Which is 1/2. And then we have a g m squared r squared, right? Same thing for F5. We now have a factor of 5 times 2, which is 10, over 4 squared, which is 16. So we have 10/16 g m squared over r squared. So to figure out which force wins, we have to figure out which is bigger between 10/16 and 1/2. Since 8/16 is 1/2 and 10/16 is bigger than that, this force is bigger, and so we should expect that F5 is greater than F1. And if F5 is greater than F1, we would find the net force is to the left. And it looks like they've done the math wrong, because I'm pretty sure that's 10/16, not 5/16. Yeah, I think they messed both of them up though. Like they forgot the factor of 2 there, but that doesn't matter. Okay, so next one, right? 2 small objects, they're a distance r apart. Notice there's no numbers in this problem. So our initial force is just gm capital M over r squared. And then the final force, when we change the masses, g doesn't change, right? That's a universal constant, 2m to capital M, and then distance is 4r squared. And so we just need to simplify this down. G stays the same, little m stays the same, big M stays the same, r squared stays the same. And we're left with 4, 2 times 2, over 4 squared, 16. But now we can do some nice simplification, right? This and this are the same, right? So this is just F initial times 4/16, which is 1/4. And so that means we should get F over 4. Right? Okay. So this one's a little bit more of vector math, but we're also not given a picture. So that's really a good first place to start, right? Draw it out. So 3 50-kilogram balls at the corners of an equilateral triangle. Okay, so I'll draw my best approximation of an equilateral triangle and put 3 balls at it. Okay. Let's label some lengths and masses in here. So this is 30 centimeters, and this is 50 kilograms. Okay, so now, if one of the balls, so it doesn't tell us which one, doesn't actually matter because they're all the same, so we'll go with this one. We're going to let that one go. What is the magnitude of its initial acceleration? Well, if we knew the force acting on it, we could use F equals ma to get the acceleration. And there are 2 forces, right? We have a force from this interaction, and we have a force from that interaction. And here we notice this is going to be a bit more of a pain in terms of vector math. But, right, this is an equilateral triangle, so that must be 60 degrees, so this must be 60 degrees as well, right? So that'll help us a little bit. So the first thing I notice as well is because it's an equilateral triangle, the magnitudes of the green and yellow forces are going to be the same. So I don't need to calculate both magnitudes. Oops. I do need to calculate one of them and use it twice, but I only need to do it once. So g m1 m2 over r squared. So let's plug in some numbers for that. So g is 6.67 times 10 to the negative 11th. Actually, well, I'll leave it there. M1 and M2 are both the same, right? 50 kilograms, right? And then r squared has to be in meters, 0.3 squared. Okay? So that number right there is going to tell us the magnitude of each of those force components, which we'll then have to do vector math to figure out the net force. So you can punch that in your calculation, and that calculation into your calculator. And if you do that, you should get 2 times 10 to the negative, let's see, 6th, right? So now we've got 2 times 10 to the negative 6 newtons. So we just need to do the vector math. Okay, and so to actually do the vector math is going to be a little bit of a pain. Easiest way, I think, is to take this and break it up into components, right? This angle in there must be 30 degrees, right? So this right here is 2 times 10 to the negative 6th sine of 30 degrees. And this right here is 2 times 10 to the negative 6th cosine of 30 degrees. Okay? And those angles are actually pretty easy, right? The cosine of 30 degrees is square root of 3 over 2. So this is just square root of 3 times 10 to the negative 6th. And the sine of 30 degrees is 1/2. So this is just 1 times 10 to the negative 6th. Now, to actually do the vector math, right, we add the x components, which in this case are this and then this whole green thing. So the x component is 3 times 10 to the negative 6 newtons. And the y component, there's only one of them, right? There's only the 2 times 10 to the negative 6 cosine 30, which is the square root of 3 times 10 to the negative 6 newtons. Then we need to put these components together using the Pythagorean theorem. And I'm running out of space on this page very rapidly, so I'm just going to kind of draw an arrow and not actually do the math. Right, we square both and add them up. And then take the square root. And if you do that, we get the net force is 3 times 10 to the negative 6 newtons, I believe. Yep. And so if we want the acceleration, we just do F net over m, which is 3 times 10 to the negative 6th over 50. And, oh, and I get an answer that's not on there. Oh, of course. Which is, I get 6.9 times 10 to the negative 8th. So I may have made a math error. I think it's, oops. I think it's E based on that. We'll see. You guys should check my math because I was trying to do this a little bit hurriedly. So we'll see if that ends up being it. But as you can see, it's really no different than other problems we've done. You just need to do a bit of vector math and deal with some small numbers at times. Yeah, sure enough, it's E. I must have rounded somewhere wrong. But anyway, or I typed it wrong in the question. So you guys should check that. And if you get 6.9, then I'll feel a lot better about myself. And anyway. And now I have another slide page that won't load. Okay, so with that working, finally, so we have a couple more problems and we'll move on to the last section here. So spaceship traveling to the moon, when is it no longer feeling Earth's gravity, or what point is it beyond the pull of Earth's gravity? Well, again, let's look at the equation. So we're asking when is that zero, right? That's what beyond the pull of Earth's gravity would mean. And it seems like kind of a dumb question almost, right? You look at it and you ask, when is that zero? Well, that could be zero, that could be zero, that could be zero, or that could go to infinity. And as you can see, all of those are impossible statements, right? It's never 0, so it's got to be D. This is a really important point, right? Gravity may be quite weak, but it's never going to be 0. We're just going to neglect it a lot of times in cases where the force is so small compared to other things, right? But it's never actually 0. Okay. So one other slight point, and this is something that is truly only critical if you're going to go on into physics more, but I've kind of hinted at it already, right? We have a way of calculating the mass. We've done labs like this, right? This, for example, was very similar to what I did when I asked you to calculate the moment of inertia of that disk that was rotating, right? You were finding the inertial mass, right? You exerted a force and used that to figure out what the mass must be that causes the acceleration you found. That's the F equals ma concept of mass. It's called the inertial mass, right? If I apply a certain force, what acceleration do I get? But there's another way now that we can define what mass is. And that's this idea of gravitational mass, which is how strongly does this object attract another one gravitationally? There is no reason that these two definitions are the same, right? This is about net force. This could be anything. This could be an electric force. This could be a push. This could be friction. There is absolutely no reason that the inertial mass that you calculate there is the same as the gravitational mass that you find from Newton's laws of gravity. It turns out, however, they're exactly the same. That's called the principle of equivalence. And this sort of odd relationship is what leads to Einstein's general relativity theories. The fact that this is coincidentally true in Newton's framework is not something that physicists like. There should be a reason for those coincidences. And that's what one of the things that Einstein's relativity theory was able to explain, which is one of the great justifications for why it might be plausible when it's so bizarre otherwise. So I'll just kind of leave it at that. If you have more questions about it, obviously, find time to look at Wikipedia or ask. But that is called the equivalence principle. And it is important, though, to know these terms, right? If I say inertial mass, you have to know that I'm talking about F equals ma equation. And if I say gravitational mass, you have to know that I'm talking about the law of gravity, right? That is definitely important. Right, just talked about that. Okay. So the last thing is to talk about now a bit more of a relationship between the little g from F equals mg that we have been using for gravity and big G, this new constant that's introduced with Newton's law of gravity. I'm sorry this is a bit blurry because it's being a bit laggy on loading. So we now have two different ways to calculate gravity forces. And that's, again, possibly a problem because they shouldn't be different, right? So our old way of calculating gravity was something like this, right? We have an object sitting on the surface of mass m, and we can calculate the force by doing m times g, right? And for Earth, that's great. Little g is 9.8. But for something like Mars, I don't have that memorized. I don't know what g of the surface on Mars is. And so it's not maybe as handy as it could be. However, we now have a new way of calculating the gravitational force, which is using Newton's law of gravity. We can calculate it using g m1 m2 over r squared. In the case of the Earth, right, I know both these answers. I know the mass of the Earth, I know the radius of the Earth, I know capital G, and I also know little g. So I should get the same answer both ways. That's only true if this condition is met. So now we have a way to calculate little g anywhere. If I want to know little g on Mars, all I need is the mass of Mars and the radius of Mars. And now I can calculate little g on Mars, or the moon, or Pluto, or an asteroid, or whatever I want, right? And once you know little g, you can use it just like we have in the past, right? M times little g will always work as well, as long as you recalculate little g appropriately. So this relationship is critical to remember. I believe it's on the AP sheet as well. But you should be able to sort of relate these two ways of calculating gravity. I'm going to skip over this because I'll probably talk about it a bit in class, but the video here is worth watching. It's kind of a demonstration of how you could calculate any of these things and the actual experiment that was done to do it. Right? It's a very difficult experiment, very difficult. So let's kind of put some of these pieces together. We know planet X, it's free fall acceleration, right? This right here is little g for planet X. That's what that means. So now we know the properties about a different planet, planet Y. What's the acceleration going to be there? Well, g is gm over r squared. So for planet Y, capital G does not change, right? That's the universal. Twice the mass, twice the radius. So we have a 2 over 2 squared is a 1/2, right? And this is just that. So it should be 1/2 of the acceleration on planet X, which then should be b. Right? Again, being able to reason proportionally without ever calculating stuff with the numbers specifically. And sure enough. All right, so what's the free fall acceleration at the surface of the sun? Well, to answer this, we need the mass of the sun and the radius of the sun. Then we can calculate g sun is gm sun over r sun squared. And this is one of those problems where I said you need to use that table of astronomical data. Right? Just look them up, plug them in. If you do that, you get 274 meters per second squared. Now, that should make sense, right? The sun is quite massive. Yes, it's also large, but it's very massive. It makes sense that it's a bigger acceleration because that's the thing that keeps the Earth orbiting it. Now, next question is, what does the free fall acceleration do to the sun at the surface of the Earth? This is a little bit harder, but only to make sure you're answering the right question, right? The free fall acceleration of the sun at the Earth's surface is, well, we still need g and m sun, but now we need the distance of the sun to the Earth squared. And again, that's in the astronomical data. Now you might be concerned, oh, do we need to add in like the radius of the Earth and the radius of the sun? Because that's the distance of separation of the centers. The answer is yes and no. Precisely, yes, you do. However, no, because the distance between the sun and the Earth is so much bigger that you're not going to get a different answer to like 2 or 3 sig figs, to like 3 sig figs anyway. So it doesn't really matter. All you need is the distance between the two. And so if you look up those values and calculate them, you get 5.9 times 10 to the negative third meters per second squared. And that should make sense because when you're on the Earth's surface, you're not being pulled off the Earth's surface towards the sun, right? This is much less than little g 9.8 meters per second squared. So you don't fly off towards the sun sort of through the Earth's atmosphere. Another thing that can be handy is calculating how little g changes with distance, right? Specifically, little g, the 9.8 value, is the acceleration due to gravity at Earth's surface. And if you're a little bit above Earth's surface, right, if you're a little bit, h, say 10 meters, 20 meters above, that doesn't really matter. Like Earth's surface plus 10 meters, right? The radius of the Earth is a big number. But if your height above Earth's surface is a substantial fraction of the radius of the Earth, now it starts mattering, right? The total distance from center to center is the Earth's radius plus how high you are about the surface, above the surface, right? And so you can do a little bit of algebra, right? Factor out the radius of the Earth squared, and then you notice that this right here is by definition little g, and so then you have this factor right here, which is basically telling you how much extra you add, or rather how much weaker gravity is because you're farther from the center. Right? So this is not given on the AP sheet, but just kind of keep in mind, this is the important modification, right? Add up all the distances center to center. So just a couple values to kind of keep that in mind and show how small the effect is, right? The distance between any of the thing that you're actually likely to be at, right? The ground, a mountaintop, an airplane is almost unmeasurable. But it does make a difference if you're sort of in the International Space Station, right? This is a noticeable difference in terms of how strong gravity is. All right, so in that case, right, why are astronauts weightless? Well, this is clearly not true. We just saw there was an acceleration due to gravity. This is also clearly not true. There's gravity. This is not a real force. That can't be true. Well, very small and weightless seem contradictory. That can't be true. So it's the statement of free fall, right? Weightlessness is not a lack of gravityless. It's just that you aren't feeling your weight. Remember back to our demonstrations early in the year about the elevator and the changing scale balance? Same idea here. Right, free fall. Okay, so a satellite is orbiting Mars above its surface, very far, 3 times the radius of Mars. So we know G Mars is G M Mars over R Mars squared. We want this G is still GM Mars over R orbit squared. But the radius of the orbit is the distance from the center to the surface plus the distance from the surface to the satellite, which is a total of 4 times the radius of Mars. Right? Which is 1/16 GM over R squared, right? So it should be that one, right? Don't forget it's always center to center. In this case, the radius of the planet itself matters because we're sort of dealing with numbers that are around the same size, right? The distance above the surface and the distance to the surface are about the same order of magnitude, right? Okay, so finally, we can kind of use our pieces now to sort of work backwards, right? We have right here a lot of kinematics information, right? The time it takes for a marble to fall. Now, we can use that to figure out what the acceleration is, right? So h is 1/2 at squared, right? Starting from rest, v equals 0, we use kinematics. We can rearrange this to solve for a, right? So 2 times 2 over 1.02 squared. We can plug that in and we'll get the acceleration. Which is 3.84 meters per second squared. Okay, so that must be the local acceleration due to gravity, little g. But we also know that g is gm over r squared, which we can solve for the mass of the planet, which is what we want to know. So g little r squared over big G is capital M. And if we now plug in the values we know, for little g of 3.84 times the radius that's given, 3.39 times 10 to the 6th, and square it, and divide that by capital G, 6.67 times 10 to the negative 11th. Right, plug all that in, we're going to get M is 6.6 times 10 to the, positive 23rd kilograms. 6.62, I guess, if I keep 3 sig figs, and that's option B. Right, so it's a way to experimentally determine the mass or the radius of the planet if you know one of the two. Right, that's it. So we're going to stop there on this part, right? The next part we'll talk about energy and momentum related concepts. The big key, right? This is just another force. You can add it like a vector, just like any others. You can use it to cause accelerations, just like any others. We aren't really introducing anything brand new.